Great stuff. We are starting our first Zoom session for 110. I've made the mistake sometimes of holding these darn things and forgetting to push the record button. And then you realize, well, gosh darn, the only people who got to hear it were the people who attended live. The whole rest of the class can't even tune in. I always record the Zoom sessions, and then what I do afterwards is I upload them as YouTubes. So I upload them as YouTubes onto Canvas, OTC Canvas.
Okay.
And that's if you go to OTC Canvas, it'll have like a dashboard. It'll show you your courses that you're taking, 110, 120, whatever you're taking, and you click under 110, and then you'll see a screen that says home, coursework, and you'll click the box coursework, and then you'll see these balls, these round things, and each one is a unit. Unit 1, Unit 2, Unit 3, and you just click Unit 1, and then you'll be able to, if you just scroll down, you'll see, whatever I type in to talk about. Today we covered X, Y, and Z. Yeah, I even said the last letter of the alphabet correctly, Z. In Canada, we say Z. Anyway, and so you'll see a link to the uploaded YouTube segment. And this isn't for you because you're watching live, these three, Audra and Shabana. You see your name, Shabana? So anyway, for those watching this live, that's no matter. But for people who tune in later to watch the recording, you've got to go into Canvas, go into what they call the dashboard where you see your courses, click on 110. Once you're inside 110, you got to go into your coursework. You'll see a box called Coursework. Click on that, and then you'll see all these round circles, Unit 1, Unit 2 through Unit 8. Click on Unit 1 for this time, and then you'll scroll down and you'll see the link to the YouTube, and that's today's Zoom session. Each Zoom session will take about an hour. So it's 9:30 here, it's 11:30 in Missouri. Gosh, probably what is it now? 12:30 in Florida. So on Eastern time, I'm on Pacific Standard Time, but no matter, I will always hold these Zoom sessions at 11:30 Central Time, the same time as we're starting today. And I'll carry on for about an hour. You guys can ask questions or what have you, and stuff and things and stuff. Now, one thing I will encourage people to always do when you are watching a recorded Zoom session is never watch it on a cell phone, because the screen is too darn small. There's a lot of times where I'm going to be showing you PowerPoint slides, and the PowerPoint slides have pictures of graphs on them and diagrams, and when someone's looking on a stinking cell phone that's about it's about this big, it's going to be hard to see. I always encourage people to sit in front of a laptop computer or a desktop computer that has a monitor that's about a foot wide so you can see what the heck is going on. That's one thing I want to mention. A second thing I want to mention is always watch the Zoom sessions, because guess what? 90% of your course material is on these stinking Zoom sessions. It's the notes in front of me that we cover, and you'll see this in your units. When you go into units in your coursework, you will see, and I'm going to this is all just what do you call housekeeping today. We're just talking about how the course is laid out and what we're doing, okay? So basically, before each Zoom session, shortly before you tune in, it's a good idea to go into the Canvas, look at what they call the dashboard, click on 110, Spring 2018, 110, go in Coursework, see the unit we're talking about. Today it will be Unit 1. Click on Unit 1 and scroll down, and you will always see two things. One's a blue highlighted phrase and the other one's a red one. And the blue one is your Microsoft Word notes for that unit. And print those puppies up. Print them up. because they're about, the unit 1 has about 1 page, 2 page. It's a 4-page document. It's got 4 pages in it, okay? And these notes are like cheat sheet. They're like your textbooks squeezed. Because I've taught this stuff for years and years, and I know it backwards and forwards and upside down. And what I've done for your convenience is I've compiled it into notes. So when you go on to the Zoom sessions like you are today, have those notes printed up. And I would even say for people who are tuning into the recorded session of today, stop the recording now and go in and print up the darn notes, and you'll see what I mean. You don't need to print up the PowerPoint. The red phrase is the PowerPoint. And the PowerPoint slides go with these notes. Go ahead.
I'm looking at the coursework. I clicked on the coursework button for HIS 110, and right now the only thing that's loaded is units 5 through 8.
Okay, I'll check with Rebecca Krause about that. That's weird, but thank you for bringing that to my attention. I'll definitely be talking to Rebecca about that. Okay.
Okay.
Good stuff. Glad you brought that up. So I'll make a note to that. I better do that right away because I don't want to forget. Just write Becca 110. Okay, good. All right. So inside of any of those units, just for the fun of it, Audra, you can just click on Unit 5, just for fun.
Yeah, I did.
And when you click on Unit 5, you'll see notes. You'll probably see psychoacoustics. It'll probably say loudness and pitch or something like that. And then you'll see notes, and you'll see PowerPoint. So the notes I would print up, and then the PowerPoint is what I'm going to be showing on my screen. I'm going to share my laptop with you. So the PowerPoint slides are what I'll do. So for example here, I'm going to share screen right now, and I'm going to go into and pull it up just for fun. So right now you're looking at OTC stuff. Look at that weird island. Do you see that weird mountain in front of you? That is actually Iceland. I went to Iceland. My wife and I went there a couple of years ago. You can see some Icelandic ponies and stuff like that. Far out, huh? Anyway, I'm going to go into my documents here, click in documents, scroll down until I get to OTC, go up a little bit. Look at that, tap, you'll see tap. Yeah, I do some tap dancing once in a while. Okay, I'm gonna move this over here, up, 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 OTC, click, and 110, click, and 110 for 2018, click, okay, see there, now look at this very carefully. You'll see 1, that's unit 1, frequency, wavelength, speed of sound. The blue, of course, is your Microsoft Word notes, and the red is the PowerPoint. And that's what I've uploaded to each of your units. There's some real, no, anyway. And then there's unit 2, the intensity and the decibel. And then unit 3, complex sounds and speech. Now unit 1 will probably take 2 to 3 weeks to cover it. Unit 2 will probably take 2 to 3 weeks to cover it. Unit 3 will take 2 weeks to cover unit 3. And then that takes us halfway through the course. Then it's midterm time. So units 1, 2, and 3 will be on the midterm, halfway through your semester. And then when we reconvene after the midterm, now look at what your courses are called. Unit 4, Psycho. Unit 5, Psychoacoustics. And Unit 6, Psychoacoustics. Now, psychoacoustics is the human perception of sound. It's just our perception of sound. So units 1, 2, and 3 are the physics of sound. Boy, there's something scraping like crazy. I keep on hearing a I don't know what that is, some technical interference or something. But at any rate, units 1, 2, and 3 are the physics of sound. Units 4, 5, and 6 are the perceptions of sound. And then the last unit, unit 7, we get into hearing aids specifically, and we'll talk about acoustics as they relate to the shapes of hearing aids. And that's called non-electronic modifications of hearing aids. And so each unit, you'll see a blue and a red, blue and a red, blue and a red. Print up the notes, and then watch the PowerPoints. If you print up the PowerPoints, you might kill a few trees, as if, you know, they'll take some space. So I just say you can access those electronically on your own through Canvas anytime you want. I mean, that's yours. But for doing the Zoom sessions, print up the notes, because that way you can scroll and write. So I'm gonna, what do you call it? Double click on notes just for fun. And the notes close up, pulled up, would look an awful lot like, well, sometime today would be nice, but I'll just wait for this puppy to pull up here. Processing, yeah, right. There we go. Microsoft Edge isn't your default. Okay, so you will see acoustics, and you'll see all these weird words here: sinusoids, frequency, period, wavelength, speed of sound, sound fields. Those are all the topics. Here's your readings out of your textbook. Okay, Lass and Woodford. So Hearing Science Fundamentals. It's a great little textbook. It's written in English. I love it. I can actually read it. It's easy to read. It makes perfect sense. I think, Audrey, you're holding one of those up there. Yeah. And if I stop sharing screen, show us, Audrey, what it looks like. Or do you have it, Shabana? There you go. Perfect. That's the book. All right. Cool. Back to share a screen here. All righty. Okay. And we'll cover stuff like the physical properties of sound over here. I'm highlighting this. And then we'll talk about what sound waves are. And we'll be moving through that. And then if you move down the middle of your page 1, you'll see sound waves, longitudinal or transverse. Now, put a star by that if you have that printed up. If you don't worry about it. Just listen for the day 1, because this is just our warm-up session, our informal blah, blah, blah session. Sound waves aren't like water waves. Sound waves are molecules in air. Water waves go from the Atlantic hitting the shores of Florida, or the Pacific Ocean hitting the shores of California. You know, your waves, water waves go up and down. Well, let me just show you what I mean, because sound waves don't do that. So I'm going to squeeze this note smaller. Is it just me, or am I hearing a train? I just hear this.
There's a truck passing by. I could try to mute.
Okay, wow, I'm just hearing this wow, boom, boom, crazy stuff. Anyway, I'll just pull up this frequency. I'll pull up the PowerPoint, and the PowerPoint slides are what I'm going to be sharing my screen most often with you. So as we go through Unit 1, and we'll look at sound waves, and I'll show you what I mean by the middle of your notes there on page 1, okay? Here we go. I'll pull up this slide just for fun and make it larger. See that slide? Sound waves are the top portion of that slide. Can you see how the tiny molecules of air get black and white, they squeeze together, separate, squeeze together, separate, squeeze together. Whereas if you look at the bottom, those are water waves, those are waves. We draw sound waves like they go up and down like water, but we do that just because it's easier. I don't feel like doing this on the top. I don't feel like doing letter A. It's too hard. I mean, how many ding-dong times do you want me to be It's crazy, okay? But sound waves don't really go up and down like this, because if they went up and down like this, we'd be going like this listening to sound. I mean, that's just nuts, okay? So that's what I mean when I look at sound waves being longitudinal or transverse. Transverse is like water waves on the bottom here, whereas longitudinal means molecules are squeezing together back and forth. So it's interesting. I think the whole field is rather trippy. So let's just take a look at the slide 1 here. Slide number 1. And I'll make it bigger so we can just see the whole ding-dong thing here. Here you see a tuning fork. And the tuning fork is going dong, and it's vibrating. Okay, someone hit this tuning fork right in the center here. And when you've hit that tuning fork, what happened was you made squeezing and separating of molecules in the air. Those are sound waves. Those are sound waves. And when you're looking at sound waves, you can say that the squeezed areas are condensed or compressed. See where it says that right here? Compression. And then you have rarefaction. So you have squeezing, separating, squeezing, separating. Those are sound waves. So each squeezing and separating is one up and down. If I show you this way, whoops, one squeezing, one separating, condensed or compressed, you can see where I'm circling, rarefacted or spread out. Condensed, rarefacted. The condensed, the wave is drawn up. Rarefacted, the wave is drawn down. And when you've got one compression and one rarefaction, well, then you have one wavelength, one cycle, C-Y-C-L-E, one cycle of sound. And when you think of a cycle of sound, one up and down, you can think of degrees. You got 360 degrees. Look, start at 0 degrees where my cursor is, 90 degrees, 180, and then down at the bottom, 270, and then over here, 360. You're now back where you started. Just like a circle. If you're going to do a 360 in the parking lot, you got the pedal to the metal and you got the steering wheel curved and you're going, you're doing a 360. Okay? A circle is 360 degrees. And so does one cycle of a sound wave. Because look at this. If you took this portion with my cursor right here and I bent it this way, I'd have one up and down. I'd have a circle. So a sound cycle has 360 degrees. One condensation, one rarefaction is one cycle of sound. All right, so you got to step into the pool in the shallow end. Because if you're dealing with hearing aids and you're going to be hearing instrument specialists, we have to know what the Sam Hill sound is. We got to know what is sound. Because we're going to be talking about sound in terms of its intensity, and it's measured in decibels. And we're going to be talking about sound in terms of frequency or pitch. All right? So when you think of all these, there's a whole bunch of stuff happening here. Just for fun, I'm going to back up now and go to slide number 1. We talked about this slide briefly. Here's another slide showing you a similar thing. Here's a sound source in the center, and it's creating a sound. It could be a foghorn. It could be somebody talking. And now you have squeezing, separating, squeezing, separating. And those are the sound waves emanating from the center going out. Just like this tuning fork. Sound from the source emanating, going out. All right? Sound waves aren't light waves. Okay, look at this picture. This picture is talking about light, not sound. So this picture here would be dealing more with optometry, if you were going to be an optician. But look at radio waves, way on the left. AM radio, shortwave radio, television and FM radio. And then you start getting into infrared. And then you get into the colors that we can see. Red to yellow to green to blue to ultraviolet. And then you get up into X-rays and gamma rays. Those are light waves. Now, I'll stop sharing for a second. Light waves can go through outer space. Light waves don't need molecules. Okay, when you look at the moon at night, you're seeing the light from the moon. It took 3 seconds to get from the moon to your eyes. When you're looking at the sun, don't look at the sun, you'll go blind, but you know what I mean. The light from the sun takes 8 minutes to reach the earth. Okay, light travels really fast, and the earth is 93 million miles away. So it takes 8 minutes for light to go 93 million frickin' miles to reach your eyes. Okay, light is very different from sound. Okay, light waves don't need molecules. Light waves can travel through outer space where there's no air. Okay, outer space has no molecules. It's just black with planets and stars in it. All right? So light is a totally different kettle of fish from sound waves. Sound waves have to have a medium. In other words, they can travel through water. That's how whales communicate with each other. Dolphins, they're using sound waves through water because water has atoms and molecules, has little particles. And sound waves can go through air because air, when I move my hand really fast, I can feel the air against my hand. So obviously there's something in the air. It's a presence. It's a gas. Okay? And gases have molecules. So great, sound can travel through air. Yep. Sound can also travel through hard objects like wood, trees, steel, railroad tracks. So when you think about the saying, someone's looking for a job and comes up to you and says, do you know where there's any work over at blah, blah, blah? And you say, you know what, I'll keep my ear to the ground. You ever heard that saying? I'll keep my ear to the ground. You know why they said that? Because First Nations Indians are native peoples of North America. They would, to listen for the buffalo coming, they would put their ear to the ground to listen for the hoofbeats because sound travels through the ground too. So, and sound travels through hard objects faster than it does through air. If you put your ear down on a railroad track, you'll hear the train coming through the railroad track with your ear on the railroad track. You'll hear it coming through that medium of steel way before you hear the train coming through the air. Okay, so the sound waves travel always through a medium. They travel through gas, they travel through water, they travel through steel. Okay, so all gaseous like hydrogen, oxygen, they travel through that. They'll travel through water, all fluids, and it'll travel through objects like my coffee cup. Okay, so anything that has molecules, sound will travel through. Light ain't like that. Okay, share screen again. Back over here. We're just kind of talking. These are light waves, but we don't care about that because we're going to be hearing instrument specialists. So this is just talking about light waves. Here's visible light again. That's just thrown in there for the heck of it. But look, not just for the heck of it. Look at how red is over on the left and the purple is on the right. This represents the frequency of light waves. Frequency. Oh boy, that's a weird word. Or my voice got weird. Frequency. Now, when you think of the word frequency, that just refers to how many things took place per unit of time. So I can talk about the frequency of my footsteps. You know, am I walking? Is it 1 step per second? 1, blop, blop. Or am I walking fast? Blop, 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 blop. 2 footsteps per second. Okay. Frequency just refers to how many times something happened per unit of time. Well, when we talk about sound, we use second. That's the time we care about, not hour, not minute, second. And we talk about how many cycles took place per second. How many of those squeezing and separatings took place per second? Well, did a whole bunch of them take place per second? If they did, you hear a high-pitched sound, treble. If only a few took place per second, you hear a low-frequency bass sound. Okay, so when you think about low C on a piano, or a foghorn, let me stop sharing and I'll show you a picture here. Just see, if you are talking about a foghorn, now look at this picture here, these compressions and these rarefactions are going to be really wide. Okay, they're going to be fat. But if you're talking about ding, a high-pitched, like a canary chirping or birds chirping, high-pitched sounds, then these squeezing separatings are going to be really skinny. Now, let's talk about sound. We said that it takes light from the moon 3 minutes to reach the earth. We say that it takes light from the sun about 8 minutes to travel from the sun. to hit your back of your eyes. How fast does sound go? Yeah. Sound is a creepy crawler snail compared to light. That's why you see the lightning way before you hear the thunder. You have to see and wait a few seconds of the clouds. Sound is slow compared to light. Sound goes about 766 miles an hour. So when you think about that, have you ever flown in a jet? A jet, a 747 jet with a tailwind flies about 600 miles an hour. Okay? In Canada, we call that 1,000 kilometers an hour. 600 miles is 1,000 kilometers. Everywhere in the entire world uses metric except the USA and England. You guys. I always laugh a lot. Let me just say, here's my little chuckle. What's freezing in Florida or freezing in Springfield, you guys call it 32 degrees. We call it 0. Boiling south of the border is 212. We call that 100. This way it makes way more sense. Like, to me, I'm a little biased, but we've given up on inches, feet, miles. We talk centimeters, meters, kilometers, because everything's on 10. Everything's based on 10. So it makes it easy peasy Japanesey to figure it out. But at any rate, science uses metric, even in the USA. So as soon as you get into physics and start studying chemistry or physics or biology in the US, they talk metric. So metric is the language of science anyway. But at any rate, sound goes about 766 miles an hour, or about, I think, 1,200 and some kilometers an hour. So when you think of that, now let's talk about light. How fast does light go? Light travels about 186,000 miles per second. 186,000 miles per second. So if you wanted to figure that out, how fast does sound go per hour, I guess you'd multiply 186,000 times 60, and then you'd multiply that by 60 again. I think you're going to get to something like 6 trillion. I think you'll get to some number like 6 trillion miles an hour, some stupidly huge. And then now look at sound, 766 miles an hour. So this just tells you, again, the whopping difference between sound and light. There's 2 things to note here. Light goes way faster than sound, and the second thing is light doesn't need a medium to travel through. It can go through outer space. Now, if we were in outer space, us 3, or any of us, and we're floating around in outer space, and you could yell all you wanted, no one's going to hear you. It could be screaming your head off. No one's going to hear you. Even if your face is 1 inch away, you're not going to hear me because there's no air to travel through. Okay? It's just something to think about when we talk about sound. I'll share screen once again, and now we'll take just a bit of a peek at a PowerPoint slide here. Okay, I should say at your notes here. Let's just talk about what we talked about from your notes. Okay, so I'm going to scroll down with the notes here, or scroll up, and I'll talk right from the very beginning. Sinusoids. What the heck is that? Well, think of your sinuses behind your nose. Sinus means bends or folds. Well, sinusoids, sound waves. They're bent. We draw them like bent, okay, like folds. That's why they call them sinusoids. So in your texts or in your readings, anytime you see sinusoid, just think sound. Same thing. Sinusoids, frequency, period, we'll talk about that. Wavelength, how long are the sound waves? And we already said bass has long sound waves, treble has short sound waves. We talked a little bit about speed of sound. We haven't talked about sound field. Well, sound field just means any kind of a room or space in which sound takes place. So over at Audra's house, I can see her there. The sound field around her is that room. And Shabana, the same thing. That her sound field is that room around her. Okay? Sound field just means the area in which sound takes place. Could be a classroom. And then you have the last thing called resonance and impedance. Now, resonance and impedance, I'll stop sharing for a second. Resonance just means an object's favorite vibrating frequency. Now, the favorite vibrating frequency of an object. So now if we think about a wine glass at Christmas, and you're holding up a glass, and it's got a bit of wine in it, you lick your finger, and you're around the rim of the glass, much like I'll pretend I'm doing that here, and the glass, that's the resonance of that cup. Okay? Or when you take a pop bottle, and you blow over a pop bottle, and now you've hit the resonance of that thing. Resonance is the favorite vibrating frequency of an object. And guess what? Your ear is an object. And guess what? It resonates because it has a certain shape. All right? Every object has a certain amount of mass, like density, like, you know, what's its weight, how thick is it, how dense is it, and every object has a certain amount of stiffness. Now, if you think about yourself listening to TV in your apartment, and the neighbors upstairs are playing loud music, what's going to come through your ceiling? The bass guitar and the drums, because boom, 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 because your ceiling has lots of mass. And mass resonates with low pitches. So what's going to come through your ceiling? The bass, guitars, and the drums. Okay, think of a train, a locomotive, a great big heavy frickin' locomotive. Do you think you're going to be able to jiggle a locomotive? You're going to have 100 people push, and then you're going to have same 100 people pull, because mass doesn't resonate with high pitches. Okay, doesn't like moving, hates it. Okay, so heavy things will carry or will resonate with the low pitches of sound. Whereas, if pretend I have a thick metal spring sticking out of the wall. So I'll stand up here and pretend I've got some huge, heavy spring sticking out of the wall here. Okay, if I grab that spring and I try to push hard and pull hard, I'll run into a lot of resistance. But if I stand there and go, easy peasy Japanesey. All objects have mass and stiffness. And mass and stiffness together create the resonance of an object. Okay? And your ear, let me take this home, because it makes your ear, the shape of your ear, the reason your ear has the shape it does is because it resonates, get this, with speech. Okay? And you think of the word speech. It's got speech. Okay? You've got speech. Those are high pitches. And in speech, E from your throat is relatively low. Just for fun, since I have you two here, put your hand on your throat and say, ah. You feel that vibrate? Say M. Feel it vibrate? Good. Now say the letter S. S. No vibration. Say the letter F. No vibration. Say the letter CH, as in church, no vibration. See, speech has low pitches and high pitches. The vowels of speech are low pitched. And guess what? Hearing loss mostly involves treble. Elderly people who need hearing aids have trouble hearing treble. They don't have trouble hearing bass. They can't hear the birds. They can't hear These sounds, CH, they can't hear F. They can't hear TH. They can't hear those. Okay, now think about these words. I'm going to say several words to you. Hat, bat, fat, cat, sat. What do they all have in common? Ah. What makes them different? High-pitched. Your ear resonates with the consonants. Not with the vowels, consonants. And consonants in speech tell you what the word was. Vowels tell you that a word is spoken. Vowels are cheap. They're worth about a dime. It's the consonants that tell you everything. They tell you whether you said kittens or mittens. They tell you whether you said fat or cat. They say everything. And those are treble sounds. And your ear naturally resonates with treble sounds to help you hear them better. That's why your ears are shaped the way they are. Okay? But when you're losing treble hearing, that's not good enough anymore. It doesn't help anymore. And what happens is, what do elderly people say? You young kids mumble. Kids mumble today. And that's because they can hear, but they can't hear the high pitches. They can hear, but they can't hear what you said. Words that rhyme give them trouble. Okay? So they're always trying to figure out what you must have said. Oh, you're washing dishes? Okay, you're talking about, soap or whatever, or you're doing this? Oh, you must be talking about, they're always trying to play catch up. And because they're always trying to play catch up, you get tired doing that. Finally, they say, why don't you guys go on out and read, have fun? I'm going to stay back and read a book. Hearing loss leads to isolation and loneliness. So all of this stuff ties together. Emotions, your psychology, relationships, and what does it all boil down to? Sound waves. Okay? Physics of sound. High pitches, low pitches, length of sounds, short wavelengths, speed of sound, all of this stuff. So it's a huge world. It has an objective physical component, but you're also going to be taking a course in counseling. So the whole gamut of this field is really cool because it has science and it's got art. It's got a mind and it has heart. There's a real mixture or a fusion. And this course is mostly the science. And a lot of people get freaked out about acoustics because they think, oh my God, it's all math. No, it isn't. You know what? The most math we're going to do in this course is addition, subtraction, multiplication, and division. No calculus, no algebra, no trigonometry, no geometry, okay? But still, people freak out because they think, oh, okay, I might be asking you like this, 5 over 1 is equal to 10 over x. And I'll be asking you to find x. Okay, I'll just cross multiply. All right? And that's what you're going to be asked to do because you need to figure out what is the frequency or what is the wavelength. And I'm going to ask you to calculate that at times. But all it's going to require is, just very simply, it could be like 5 over 1 is equal to 10 over 2, or 2 over 1 is equal to 10 over 5. It's as simple as that. So, but it's that kind of arithmetic. That's the max. So it's probably 6th grade arithmetic is the maximum that you're going to be asked to really do. But by gum, you're going to have to do it. And there's some people who just don't watch the Zoom sessions. And when you don't watch the Zoom session, you're screwed. You will probably fail the course. And if you watch these puppies every week, you got it made in the shade. The lowest grade you're going to get is a B. I swear to God. There's a lot of people that don't seem to, they just sort of sweep it under the rug. So I'm laying it out really thick on day one here that the Zoom sessions, whether you watch them live, doesn't matter. Some people are working or have kids or whatever and can't at the time that I'm delivering the Zoom session. Who cares? Go on to Canvas. Go into Unit 1, and you'll see the unit. You'll see the link for the YouTube at the bottom of Unit 1 or whatever, because I upload, as soon as I'm done this, I have to upload it onto YouTube. And once it's saved as a YouTube, then I have to create the link in your Canvas units. And so I usually send out an email too. I think Lynn Royer also sets up something called Remind, R-E-M-I-N-D, and that's yet another way that I can get a hold of each of you. That only allows me about 140 characters, something like Twitter, but I can just make a short, quick announcements that way too. So I might set up a Remind group for 110, a Remind for 120, but otherwise always check your OTC emails. Okay, since you're taking an online course, I don't send any emails to personal emails because I haven't got the foggiest notion what they are. And you know what? If I take them all down and write one letter wrong, the person doesn't get it. So it's easiest if I just send it as a group email to your OTC emails. Okay? We're all good. All righty. Stuff and things and stuff. How you doing so far? All right? Cool.
Yeah.
All right. Here we go. Share screen. And we got another 15 minutes to go. Look at how time flies when you're having fun. All right. In this course, read from the top. We will cover the physical properties of speech. I'm going to highlight it in gray here. Physically, sound is look at that weird sentence. Sound is a propagated change in the density of an elastic medium. In English, that means sound is a forced change in the density of molecules. Just like that tuning fork that you saw. Let me just ask you a question here. If a tree falls in the woods and nobody's there, is there a sound? You've ever heard that weird riddle before? A tree falls in the woods and nobody's there to hear it. Is there a sound? Well, what's the definition of sound? A propagated change in the density of an elastic medium. Well, if sound is this, okay, guess what? I guess there is sound in the woods if a tree falls and no one's there to hear it, because sound is a propagated change in the density of an elastic medium. Sound made molecules into patterns. Did that happen when nobody was there to hear? Yep. So I guess the answer to the riddle is there a tree, when a tree falls in the woods and no one's there to hear it, is there a sound? Yes. Okay, we solved that one. Next. Psychological perception of sound is called psychoacoustics. We'll take that after the midterm. Psychologically or perceptually, sound is an auditory experience, the act of hearing. Well, let me just say this to you. I'll stop sharing for a second. In psychoacoustics, what we mean is we hear some frequencies better than other frequencies. So we just do. Our ears resonate with some frequencies and they don't with other frequencies. Cats have different hearing than dogs. Dogs have different hearing than humans. So how do humans hear sound? That's what we want to know, okay? Because you're going to be testing hearing on humans. Right ear first, left ear, and humans, we have to find out what the bottom level of human hearing is, and that's the field of psychoacoustics. But first, before we do psychoacoustics, we have to learn what the heck sound is in the first place. Look at this one here. Anatomy and physiology of the ear sits between your psychology and the physics. The physics is what we looked at today. The psychology of it is your perception of sound. And what sits in the middle of that is the anatomy of your ear. Okay, so the physics of sound plus the anatomy and physiology of your body leads to your particular sensations of sound, psychoacoustics. Next one here, simple wave motion in air. Brownian motion has nothing to do with the color brown. Okay, Brownian motion means random movement of molecules with no sound. It's just the random movement of molecules with no sound. As soon as you strike a tuning fork, boom, you got a pattern. As soon as you make a sound, boom, you got a pattern. Notice here you have a pattern. Condensed, rarefacted, condensed, rarefacted, condensed, rarefacted. And these are traveling outward at 766 miles an hour. Okay? So now you have a pattern. That's not Brownian motion. This is sound. Back to your notes. Propagation, strike a tuning fork. Something has to cause or propagate an abrupt change in the random Brownian motion. And then the rest of this stuff, blah, blah, blah. Fork tines continue past the center due to inertia until elastic force, blah, 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 blah. What I want you to hold here is write in your notes on the side here or on a piece of paper beside you, there are two things that affect the resonance of sound. There are two things that all objects that carry sound have, okay? Mass and stiffness. Mass and stiffness, they determine the resonance of an object. Mass is sometimes called density. Mass equals density, okay? Stiffness equals elasticity. Now you would think about that. Think stiffness is elasticity. Elasticity? What the heck are you talking about, Ted? Elastics are rubber bands. They're not very stiff. I'll stop sharing for a second. Elastics, snap, okay. But in physics, elasticity means the ability to resist being bent. In other words, elasticity in physics means stiffness. Stiff as a board. So every object has a certain amount of stiffness, like my coffee cup, and this coffee cup also has its own properties of mass. My glasses have a certain amount of stiffness, a certain amount of mass. This light, okay, everything, the air around you, whatever sound travels through has its own mass and stiffness, and that determines everything when it comes to sound. Those are two terms that on day one I just want us to focus upon, so that because you'll hear about them again and again and again. The bottom here says sound waves are a series of squeezed and separated, and the words are condensed and then spread out molecules. The next section we talked about water waves versus sound waves. Let's read this together. I'll scroll here and just highlight it. Sound waves, longitudinal versus transverse. Transverse waves are like waves of water. In other words, the molecular motion is perpendicular to the direction of the wave. The wave is going up and down, and the wave is also moving this way. Okay, so the wave is going toward the shore, but the up and down movement of the wave is perpendicular to the direction. Okay? Longitudinal waves are how sound travels. In other words, the molecular movement is doing this, and the wave is traveling in the same line. So parallel, in other words, not perpendicular. So the molecular motion is in the same direction as the wave. We draw sound waves up and down like bumps because it's easier. We draw sound waves like bumps because it's easier. And that's this slide here. We do it because it's easier. But please don't think sound waves go up and down, because they don't. Water waves go up and down. Those are transverse waves. Sound waves are longitudinal waves. Look at this picture. It's showing you a speaker. I'll just show you pictures here as we complete day one of Unit 1. Okay, here's a speaker, and it's emitting a low-pitched sound. See how it's rarefaction, condensation, rarefaction, condensation of molecules are wide. And here's how we draw its sound wave. Okay? Now look at the bottom speaker. It's emitting a higher pitched sound. So its condensation rarefactions are smaller. Now, so we draw them like this. So each up represents the dark. Each down represents the white. Always remember that. On a sound wave, the up represents the condensed, the down represents the rarefacted. And remember this, and remember it well, all sound waves travel the same speed. Okay, the low pitch sound is going 776 miles an hour, and so is the high pitch. Sound waves all travel the same speed, otherwise it would be one mean acid trip listening to somebody. You'd be, it'd be nuts. Okay, all sound waves go the same speed. But the wavelength, see the wavelength. So look at the picture here, and you can see the wavelength. Let's start from this top all the way down to this top. So now we've gone 360 degrees. Once you end up where you started, you've gone 360 degrees. So from here to here to here, okay? Or the bottom one, from here to here. That's one wavelength. Let's see how short that wavelength is? From here to here. There's another wavelength. From here to here is another wavelength. Whereas this guy, from here all the way to here, that's one wavelength. Okay? From here all the way to what would be the next one. So let's pretend this is 1 second, distance or time. Let's call this time. If this is 1 second from here, whoops, from here to here, how many wavelengths do we see? Well, I see 1, 2, 3.5. How many wavelengths do I see here? 1.5. Okay. We call the number of cycles per second is called hertz. H-E-R-T-Z. Just like in Hertz rent-a-car. Okay? Hertz. And it's usually drawn as capital H, little z. Okay? HZ. So hertz means number of cycles per second. Number of wavelengths per second. So if you had 3.5, as in that one there, that would be 3.5 hertz. So showing you here, this would be 1.5 hertz, 3.5 hertz. It really hurts. I'll show you another one here, just for fun. We'll just go to another one here. Showing, oh yeah, look at this guy here. Look at the top one. How many, let's pretend this is 1 second. From here to the left, over to here. How many cycles do we see? 1, 2, 3, 4, 5, 6, 7, 8, 9.5. I guess that's 9.5 hertz. Okay, let's look at this one here. 1, 2, 3, 4.5. 4.5 hertz. What about this one here? 1, 2, a little bit more than 2 hertz. Hertz means number of cycles or number of wavelengths per second. All right, and we will finish today talking about human hearing. What do humans hear? We hear as low as 20 hertz. That's the lowest we can hear, because now you're starting to just downright feel it. It's like, okay. And the highest pitch or the highest frequency we can possibly hear is 20,000 hertz. 20 to 20,000. Now, as we age, now you're 10 years old, you can't hear 20,000 anymore. Now you can just hear 18. By the time you're 20, you can't hear 18 anymore. Now you can hear only about down to 16. By the time you're 30, you can't hear 16 anymore. Now you can hear about 14,000. And so you can see what I mean. You keep losing the high pitches. Finally, by the time you're 65, now you're beginning to hit the pitches of the letters F, S, CH, as in speech, church, fish, catch, and you're starting to lose your ability to hear those. And those sounds are around 6,000 hertz, 4,000 hertz, okay, 3,000 hertz. You're starting to lose that stuff. And you know what they call that? They call that trouble hearing treble, but the name for it is presbycusis, just like the word Presbyterian church. Presbyterian means church of the elders, as opposed to the deacons. Church of the elders, okay? It's the church, Presbyterian church. Presbyopia means my arms aren't long enough to see the page. I can't see close up anymore. I have to hold things further away to see. That hits you when you're 40. That's why I've got reading glasses, because I'm more than 40. So I can't see squat close up. If I look at this, I have to put my glasses on to see it close. I can see far away, no problem at all. Zero problem. I don't need glasses to see far away. I have presbyopia. When you're 40, that means, oh yeah, you have difficulty seeing close up stuff. When you're 65, you get presbycusis. That's trouble hearing trouble. P-R-S-B-Y, presby, cusis, C-U-S-I-S, presbycusis. Presbycusis is the most common hearing loss in the world. Everybody gets it. Okay, it's international. It's going to be the same in China as it is in the US. It's international. Elderly people lose treble hearing, and they have trouble hearing what you said. Why? Because they can't hear the consonants as well. So they always need the context of the situation to figure out what you must have said. Well, I think it's been a slice. It's got 1 hour here done. Done your first Zoom session. So I encourage you to read your notes a little further for next time. Always have this. We're going to spend 2 more weeks on Unit 1, okay? Because we got 4 pages and we just went down page 1. But we're going to cover frequency and period next time. We're going to cover frequency and wavelength next time. Frequency is measured in hertz, capital H, little z. Hertz is cycles per second. What's a cycle? 1 condensation, 1 rarefaction. What's a cycle in degrees? 360. Okay? 1 wavelength has 360 degrees. Sound, it takes place in 3 dimensions. Frequency, intensity, and time. We'll cover intensity in about a month. Okay, time we won't really mess with too much. It's mostly frequency and intensity. Anyway, I think it's time to say adios. Ciao. Catch you later. And any questions, type me an email, but otherwise I think we're good. As long as we follow the Zoom sessions. Your books are great for added reading. They're great to help. Your Lassen Woodford textbook is an excellent little book, and it describes things in certain ways that I don't, but the meat and potatoes of the content are in these Zoom sessions. Okay. Are you, any of you, in 120? Are you taking anatomy?
Yes.
Okay, I'm doing another Zoom session in anatomy this afternoon, and I believe that's at 3:30 Central Time. It's 1:30 my time. I'm doing anatomy 120 then. Anyway, it's been a slice, and if you tune in then, great. If you don't, I'm recording anywho. All right. Catch you later. I'll stop recording. Bye-bye.
Thank you.